I'm not sure whether this is good or bad news. The advantage after today, the math is going to be easier. But today is likely going to be the hardest math that you have in the entire program. Before you start, well, there are two reasons why I go through this math. First, I think it's kind of important to have seen it. And the reason for that is that there are some things that are simply universal in nature. And those are some of the things. The second part is not really complicated math. The math is simple. The hard part is thinking about it. And if there's one thing I wanted to learn, that I want you to learn from this course, is really that it's not dangerous to start defining things, thinking about it. You will likely not in your future career do derivations in statistical mechanics, but you will do derivations, and you will have to sit down and assume things and model things. And I think this is a great training in this way of thinking. But I want, in particular, the harder equations here, I'm not going to ask you to be able to rederive them in the exam. Second part is that there are like 50 slides or something today. I kind of expect that we won't get through all of them. So whatever I'm going to spend the time that we need for the early part of statistical mechanics. And I haven't even mentioned anything about alpha helices and beta sheets here in the title for today. If we have time for it's great, and otherwise we'll continue with that tomorrow. So I gave you a small homework task, but I didn't mail that out until yesterday. And the minute after I did it, I realized, wait a second, if I'm pretty much going to finish off statistical mechanics today, and we also have quite a lot of math to cover, it's much better to do that tomorrow. So, did you all read that mail? Yeah. So what you're going to do tomorrow, everything we went through the first week, and this, try to explain this to either to me or to your neighbor, but without using all the math. Because it's not really complicated. You don't need all the math to understand it conceptually, but as you will likely figure out, in many cases it's harder to explain things conceptually than just cite what the derivation or definition is. But just to get us restarted, I'm going to bring up these study questions anyway and try to do the same thing we did before the break. And I'm not sure, so we have one new participant here, right? So I'm not sure, did you go through the lectures last week? Yeah. So Björn and Dari also told me that to tell you that contact them and they will help you get started with the labs if you need a login or anything. But what I do to mildly force you to start studying and at least thinking about it, I'm not going to go through this. This is up to you. So take a question and start answering it. And the trick is if you start answering early, you get the easy questions. If you stay silent and wait till the end, you get the hard ones. And I won't grade you on anything you say here. You get a grade based on the exam. So, questions. Pick one, and then let's start discussing it. Number 2. 2, yep.
The first residue to the fourth.
Exactly.
To 4 away.
And that's when you say the most common helix, that is what? That's the right-handed alpha helix, yes. And the point here, if you know that pattern, it also seems very natural to realize there's one pattern that's slightly tighter wound, and then you reduce this pattern by 1, or it's one that's less tightly wound, and then you increase it by 1. The names of those other helices is kind of irrelevant. I was 1 out of 15.
What is a disulfide bridge?
Disulfide bridge, yep.
It's a bond between 2 sulfide, and it's a sort of skeleton for the protein because it's really strong.
Yeah, so the point is a covalent bond in contrast to ionic bonds and anything. And you're right that it's a skeleton, that it's strong, but why is it so important compared to many other bonds, say the peptide bond or something? Peptide bonds are important too. You already mentioned that it's a bond between 2 residues, but where are those residues located?
But they can be like
cysteine.
Yes, we said that. But the point is you have 2 cysteines that are located in quite different parts of the sequence, right? So it's not a local bond. And for this reason, they tend to reduce the entropy of the system a lot. It orders the system. So if you have a large structure, you lock in an entire structure or something with a disulfide bond or disulfide bridge. So it's not local. Right?
Number 9, when do you get a helix dipole? Says because the hydrogen bonding pattern is aligned vertically, if you imagine the helix in this direction. direction, and all of them go in the same direction.
So almost exactly right. So it's due to the hydrogen bonds, but not necessarily not the hydrogen bonds directly, right? So what is the reason why you have a large dipole in a helix is that you have lots of small dipoles, and those, well, indirectly you could argue it's the hydrogen bond, but these are due to the parts hydrogen bonding, which is really the peptide group. So the peptide groups have this dipole, and they all line up perfectly, but of course they are also the ones forming the hydrogen bonds. And related to that, you get something. Because of that, you get this item in 10, helix capping, which is what?
That's where you get a charged or polar.
Right. And why do you get that?
Because it's a dipole, so there's a positive charge at one end and a negative charge at the other.
Exactly. Well, technically it's not a charge, right? But the dipole is the equivalent of having a charge at one end. So it's at the positive end of the dipole, it's really advantageous to have a negative residue and vice versa. And you see these things very clearly in bioinformatics. Other things.
3 and 4, I think, are the same, with the component that favors is the enthalpy, and that disfavors is the entropy.
Well, yes or no. That depends a little bit when you do things. You know what? I would actually, we're going to go through this a lot either today or tomorrow. So we could actually, in hindsight, we can actually wait with that. One important thing you realize in vacuum, the energy component is really important. But we also realize the second you have things in solution, the energy pretty much cancels out. So it turns out when it comes to these free energy components, there's going to be something there is some sort of barrier initially that we need to get over. And depending on how high that barrier is, that's going to affect the rate by which this can form. And then eventually you get over the barrier, there's going to be something else that stabilizes it. But we're actually going to see it's mostly entropy for both of them, actually. But we will, in hindsight, those were stupid questions to have. We'll go through them later, either today or tomorrow. What's the historical way to get secondary structure?
Experimentally?
So what method?
Crystallography or NMR?
Yes, so I see the spectroscopy as the bottom end, and I'm not saying that in a negative way. No, but bottom end is good because it's cheap. It's super cheap. Anybody has a CD spectrometer. What's the disadvantage of CD spectroscopy?
You can't really differ between, it has to be only half matrices or only half.
Yeah, so you only see the average secondary structure content of an entire molecule. You don't get the sequence resolution. And if you would like the sequence resolution, you would do what? Yes, and why would you not? Why would you do NMR rather than X-ray?
Because you can see the hydrogen.
No, hydrogens are irrelevant for secondary structure. The difference is the two of you go and get your sample and get it to the NMR spectrometer at Stockholm University, and it's Monday today. By Thursday or so, you're going to have your secondary structure. You start to do X-ray crystallography. By November, you might have your protein overexpressed. Then you're going to need to crystallize it, which with a little bit of luck, you might have done next summer. Another 6 months later, you will have gotten time on the synchrotron in Grenoble. And just 3 or 4 months after that, so that the point is it takes years to get an X-ray structure. If you're lucky, it might not even overexpress. So NMR is cheaper and better. But what would you do in practice? Yes, because in practice, computers today get 85% correctness in secondary structure. And the problem is secondary structure isn't exactly defined. Helices and sheets are a bit fuzzy at the end, and loops and everything. As always, there are exceptions. But overall, bioinformatics does a job that's just as good as the best experimental methods. It's not worth trying to do it experimentally. And you already did that in the bioinformatics course, some of you. Why do you gain so much energy from solvating D, E, K, and R? So first, what is D, E, K, and R? I don't expect you to know these one-letter amino acid alphabet by heart, but long term, if you're going to work with proteins, it helps. They're charged amino acids. And the main reason then is that when they are not in water, you're going to pay an enormous penalty for having it charged in vacuum or equivalently in oil.
answer the first one.
Mm-hmm.
Like in the landscape, we have the different states that we can have. So for each state, we have an energy and an entropy. So that's why it's related, because we have the differences that occurs in energy and entropy in each state.
Yes, almost. I would even say that an energy landscape, that's the continuous distribution of energy as a function of, ideally, in this case I actually didn't say what the landscape is, but the extreme case, this would be as a function of the microstates, right? So that each point in the energy landscape would correspond to one microstate. Then there might be some and again, each such point has an energy. Some of them are going to be favorable, others are going to be unfavorable. And then regions of the energy landscape that we can somehow group into a state that we can observe, say a folded state, which is not really just one point, it's a collection of states. The entropy there enters so that how many microstates are there like that. So you can say that entropy is kind of related to exploring the energy landscapes, what part we will explore in practice.
I have a question about
Yeah.
energy. How do you compute an energy landscape
That's a very good question. How do you think?
for protein? I really don't know. That's why I'm asking the question.
So the problem is that this is hard, of course. Computing an energy landscape for, say, one residue, it's easy. You can just throw it in a computer and calculate it. Say a dialanine peptide or something. And we can even, the accuracy you get in a computer there is going to be less than 0.1 kilojoule per mole. So it's going to be beautiful. And you're going to do, this week you're going to do 3 more labs on this very simple systems deliberately, but starting from next week, we're going to move you over and start doing computer labs on real proteins with modern simulation programs. You're actually going to calculate real energies on real structures and simulate them. So the beautiful thing, doing this on one residue, trivial. Doing this on 1,000 residues or even 100 residues, the problem is that your conformational landscape explodes. So if you just have one residue, it's going to be, say, 100 by 100 states. It will take, doesn't matter what, you can even do it with quantum mechanics. It's going to take a couple of hours in a computer. So the problem here is that with 1,000 residues, it's just as simple, but you don't have time. It would take 1 billion years to calculate on a computer. So you can't. You can't evaluate the complete energy landscape for a system if there are too many degrees of freedom. Bad luck. But that doesn't mean that we should give up. I'll come back to that later today, because this touches on a very important question in this lecture.
So maybe related with that, the question
13. Difference between states and microstates. Yep.
because in a state we have an entropy, and that entropy is related with the number of microstates that we have in that state. So as much more microstates,
Yes.
higher the entropy.
So the one problem with this, of course, physicists in particular and scientists, we're not always good at separating between these. So first, whenever we're working on a problem, I typically call them states. Because if I'm working on something particular, usually you only work with one type of states. So if you should be really careful about this, you should call one of them, say, macro states. And that would correspond to something macroscopically an observation you can do in the lab, say the temperature or the energy of a system. Now, exactly how the systems looks on the inside, on the atoms, or so, you don't care, because what you're interested in your experimental observables that characterize the state of the system. While the microstates are how all the particles, all the components of the system are distributed. And in general, there are billions of microstates that represent one macroscopic state.
Is a macrostate then an average of the microstate?
Exactly. Or you can say that the observables you get in a macrostate is an average of the observables in the microstate, of the properties in the microstate. Number 8, tryptophan. What's special with it?
Is the useful biophysical property the fluorescence?
Exactly. So, and the reason there are 2 reasons why that fluorescence is important. Fluorescence in general is, of course, nice because it's something you can observe experimentally. But had it been alanine that was fluorescent, we would have had another problem.
Too much of it.
Exactly. So every single protein would have fluorescence, and you would have fluorescence in 50 different parts. The neat thing is that tryptophan is so rare that most proteins might have 1, potentially 2 tryptophans. And if you mutate out one of them, you only have 1 tryptophan in your protein. And this fluorescence then depends on the environment of the tryptophan. So then you can use this to study properties locally in the protein. And while things like this might sound very detailed and low-level biophysical properties, you should be aware most of the things that you later on are going to work with, say high-throughput sequencing or something. How do you think you detect sequences in high-throughput sequencing? It's normally not direct tryptophan directly, but it's fluorescence. So every single way you need to derive data will somehow have to depend on an observable, right? And all these observables come back to this. It actually turns out in high-throughput sequencing, you're also going to have this problem. How do you can't detect every residue because that would be too slow. So you start trying to detect combinations of 2, 3, 4, or 5 residues. But then you also, how do you tell these apart? And then you end up having all these statistics between different states and everything. I don't think you're going to go through that in that course, but anytime you do measurements, you're going to have to worry about states in principle. Let's see. Do anything else that's fun here? Beta sheets, twisted, and why is the right-handed alpha helix by far the most stable helix?
I don't know, why wouldn't a left-handed helix?
So that's one question. Why is the right-handed more stable than the left-handed?
Just because of evolution.
Well, that's because of the chirality of the amino acids, right? The amino acids we have happen to be more stable with right-handed alpha helices. The reason why the alpha helix is the most stable is that it fulfills all these hydrogen bonds and it's relatively relaxed. So all these other two helices that are strained, either because it's wound too tightly or not wound hard enough. So the larger helix is essentially going to have vacuum in the middle of it. And the 310, the tighter helix, is going to be a bit strained in all the bonds. So it's relaxed but has all the hydrogen bonds. And maybe we should finish off with these things based on the labs. Multiplicity relative to microstates and entropy. Do you remember that?
So multiplicity is when you have more than one microstate that are defined by the same energy barrier.
Mm-hmm.
So they're effectively the same microstate, but they somewhat add entropy to the system because it's not the same thing having one microstate. It's like having a bigger microstate. I don't know, it's like the volume also.
Right, so the whole point is that simply if you want to go to a state with a given energy, there's more than one way to do it suddenly, right? And that's something you have to account for. And I forget whether it was Björn and Dari that explained to one of them, and I like that explanation. With this, if you are in a given state, there are different probabilities to moving to different states, right? And if I am at an energy 5, you can argue what is the probability of moving to another state with energy, say 6 or 4. But if there are suddenly 10 states with one energy, but only one other state with if there are 10 states with energy 6, but one state with energy 4, in principle, moving up in energy is bad, right? But on the other hand, it's still a finite probability. It can happen. But the more states like that there are, the larger the probability that I will go to one of them. But in the lab, you will still just observe that as one macrostate with energy 6. But this all means that this whole multiplicity is something we need to take into account when we decide how probable something is. Even if it's not the best possible states, if there are lots of states like that, collectively, this macrostate can still be likely, even though each individual microstate is less likely. And that brings us to the last one. Based on that, how would you explain entropy?
It's related with this number of microstates that you have in one macrostate.
Exactly. Or if you try to explain that without using those advanced definitions.
Okay, so entropy is related with the number of ways that you have to be in one place. So if you have more ways to be in one place, you have an higher entropy. If I have more ways of sitting in this chair, I have a higher entropy than if I stand up.
I think that was a good way of saying it. And I would just add one thing, experimental observation, right? So that there are more ways to represent the inside of the system that corresponds to one given way of having the outside of the system, say the observation. And the point is that right now we're not at all thinking about things like, for instance, disorder or anything, the way that you typically try to introduce entropy as a phenomenological term in chemistry or something, but it just has to do with, it's basically probabilities, the number of ways we can arrange something. We had a bunch of these things with hydrogen bonds. I won't go through this in detail. And my point here is basically all these processes you do or something, we can relate to what are the changes in enthalpy and what are the changes in entropy. And similarly, you can repeat that inside a protein too, and I won't really go through that in detail either. But the difference we have, in vacuo, all things look really simple. And in vacuo, at least the first approximation, unless the molecule completely changes, we're likely not going to change the entropy a whole lot. But in vacuo, if you form a bond or something, it's almost always a change in enthalpy, that you gain energy from enthalpy from doing something. The caveat is that the second you have water or a solvent around it, we screw up everything in the sense that we're usually just redistributing bonds and everything. And in general, again, that means that the energy is exactly the same, but you're talking about differences in entropy. And that's what's going to come back to protein folding. So what I'm going to do today is that we're going to get back a bit to the foundations of statistical mechanics. And there will be some math here, but what I want you to think about are these questions we're going to try to answer. So first, what do we mean by a state, and what do we mean by the things that we're still playing around a bit with it and trying to cover this in normal words? The probability of observing a system in a particular state. What do we mean by that? You might remember that I did this hand-waving derivation of the Boltzmann distribution and everything. Today, we're going to do something pretty cool. We're going to derive the Boltzmann distribution for a general system that we don't know anything about. And the reason we're bringing that, you don't need a whole lot of advanced mathematics to do this. The hard part is that you don't know anything about the system. And this is, for some reason, we usually don't do this a whole lot in undergraduate teaching. If you don't know anything about a system, it's going to be up to you to start defining things. What is the energy? What is the number of state? And the worst thing that can happen is that we do something wrong and then we might have to go back and change it. I will make a small confession that I know how to do this. I'm usually not going to screw up. I might make some typos or something. That happens all the time. But the point is, it is not dangerous to assume something that turns out to be wrong. The worst thing that can happen is that you have to go back and change it. And this is something that you should learn in the long term. Don't be afraid of starting to assume and play around with the system, no matter what the system is. What this will help us to answer, in addition to the questions that how likely is something, there's something that I keep bringing up that we haven't really defined. What is stability versus instability? And you probably know this with a gut feeling that stability is somehow the system that's happy where it is. Instability is a system that's going to move to another state, but that's a pretty unphysical definition. And that in turn will then bring us to some things. What are transitions? What are the barriers? How is that related to free energy? And in particular, this will allow us to start looking at kinetics, because there is a fundamental difference here. The Boltzmann distribution, there are two parts of it. The Boltzmann distribution tells you what are the states of things at equilibrium. If a free energy of one state is lower than another free energy, you're going to be in that state. It's more likely. You will have some population in the other state, but it's clear that an individual particle would long-term prefer, on average, to be in the better state. But that doesn't mean you will get there instantly, right? Because there is also a matter of, the question is, can I get there? And if there's an infinitely high energy barrier or something, even though in theory it might be better on the other side of the wall, if I can't get through the wall, it doesn't matter. In physics, this is kind of irrelevant because in the long run, things will go to equilibrium. The only problem is that in the long run, we are all dead. So in biology, kinetics matters a whole lot. How fast do things happen? Do they happen fast enough that it's biologically relevant? And in some cases, things happen so fast that it effectively happens instantaneously. And all these things are going to be super important to understand things later. We will come back to this, our friend, the partition function, which relates to your question about when can you determine the entire free energy landscape or something. And then I'm going to talk a little bit about phase transitions. And I deliberately haven't said anything about helices and sheets because I don't think we will get there. So if we go back to statistical mechanics, for some reasons, no, there are good reasons. Statistical mechanics has its reputation for being complicated, difficult, and everything. In many ways it is. It is extremely difficult if you were to try to formulate the equations of every single particle here. And if you try to zoom in on a square centimeter or something on this picture and try to describe all the interactions of that particles, and then you multiply that by whatever, 2,000 particles or the number you have here, that gets complicated. In theory, you could do this in a computer today. That usually works much better, and that's in part why we can use statistical mechanics for more complicated systems today. But the point here is, of course, we're not looking at the square centimeter here, right? Because if you look at the square centimeter here, either on the left or the right, there isn't necessarily going to be a substantial difference. But to you, I think it's very easy for you to tell that there is a difference between the left and the right side here, right? And that has to do with these averages that we're talking about. There is some average order on the right, and on average there's more disorder on the left. So the whole idea with statistical mechanics is that for realistic systems, such as the ones we have in biology, but also in physics, water, you have a huge number of particles. Not a million, not a billion, but think of a mole or more, 10 to the power of 25 particles. And this means that you can no longer study individual properties. We can talk about an average individual property or something, but as a system, the only thing that really matters to us is what is the average properties of the system, say the density or the energy per particle on the left versus the right. And that also by definitions means that we cannot study each and every individual state. If you just think, and again, this is a tiny system, right, compared to the ones we're going to look at later. But if you try to imagine every single possible conformation of every single possible particle here, it's going to be an astronomical number. So there's absolutely no way you can study each and every individual microstate, so you can't even observe them. And this is why we somehow need to use statistical mechanics to go from these microstates to the macro states that we can observe experimentally, such as density or something. And this means that, exactly as many of you said before, that we start looking at average properties. And the second you have average properties, this concept of entropy also matters. Because entropy is really the connection between how many microstates will give rise to this macrostate, right? That's the connection between small and big states. And that suddenly gives us a very, why, when we define entropy, the entropy we typically define as some constants times the logarithm of the microstates. Why is there a logarithm there? You just trusted me when I introduced that before. I said this is our definition, and of course, you can define. The nice thing with physics is that you can define things almost any way you want. The worst thing that can happen is that if you define it in a stupid way, nature will punish you because you end up with very complicated equations. So why did we put a logarithm there?
Because you can add logarithms.
Exactly. I'm not sure where you did this in the bioinformatics course. That if you imagine the number of states we have here on the left, let's say we can call that x1, and then that corresponds to the number of ways we can organize the left side, and then the number of ways we can organize the right side would be x2. The number of ways we could then organize the entire system, that's just probabilities, right? And then we should multiply x1 by x2. And then we keep having these multiplications. So if you have two systems that you do something which we're not used to thinking in terms of multiplying, we want to, if you double the size of the system, we like to put a 2 in front of something. And by having a logarithm, we can suddenly call this entropy, and the entropy for the total system here is the left side entropy plus the right side entropy. I'm not sure, did you in the bioinformatics course that some of you took, did you go through the definition of these alignment scores or something?
No.
Okay. But the point, you do exactly the same thing there. An alignment score is really rated. What is the probability of putting one residue next to another residue? And if you do this for an entire sequence, that's just a gigantic multiplication, very long multiplication. That leads to two problems. First, you're going to have to start multiplying a lot. Second, these numbers will be so small that you will frequently run out of the floating point domain of the computers. So there too, it makes much more sense. Take the logarithm of it and add the numbers instead. But that's a completely arbitrary definition just because we like to make our life simpler. I bet that the person who first did tried without the logarithm first, and then he went back and realized that it's much smarter to do it with the logarithm. The other part that leads to is what is temperature then? This is a hard question, I don't expect it, but think about it. We don't know anything about what does temperature really measure in a system? if we think of that in terms of microstates versus microstates. So in a way, temperature describes the interchange between states, right? If you have a high temperature, you have lots of different, then you have more energy in the system, and there are more ways that we can arrange things relatively in each other. So high temperature is somehow describing of how much freedom we have inside these states related to the energy. And that also means that if there is no temperature, by definition, we only have one microstate, and then there is no entropy.
Can I just make a question?
Mm-hmm.
If we have more temperature, will we not have more entropy than more energy? Because energy, like temperature breaks bonds, so then.
We'll come back to that in a little bit. But the whole way, it's a good question. But the point is that entropy, energy, and temperature are connected to each other, right? You might remember these definitions, and we'll come back to this definition. This was deliberately a bit hand-waving, but they're not three separated. So temperature is something we're used to think about, well, in the lab or something, but here it's not an independent quantity. Temperature really measures how much the entropy, S, changes relative to the energy of the system. And we're going to calculate exactly how much in a second. So this brings me to the mathematics. I've stolen some pictures from the book here. What I like here is that we don't know anything about a system. We're just going to consider a system with a capital S. This system can be absolutely anything. And this is the hard part. So what do you do when we don't know anything about something? Well, in principle, we could do what we did before in the course. I could assume that this is a column of gas or something. But the problem, the second I assume something, the derivation is no longer general, right? If I assume something, then the derivation is only valid for the case that I've assumed. So if I want something to be completely generic for any system, I can't assume anything about the system. What we talked about before the Easter break is that physicists usually love to think about these large systems or something where the energy is conserved. So that we're not exchanging any energy with the surrounding world. And so you can think of this. The big square here is either our lab, or you could think of it as the universe or something. It doesn't really matter, but it's some sort of large system. You could also think of this as a large, completely isolated solution with a protein in it. And the point is that once we get here, at least the first approximation, there is nothing that comes in or out here. But we're also going to look at a much smaller part. So this is the part we are observing. And you could think of this as your protein. You could think of this as an individual atom that we're looking at or something. So that here's a small system and here's a large system. And the reason in physics, when we say that the energy is conserved or anything, we typically call this large system the thermostat or something. So that the small system can exchange things with this larger system, but the larger system doesn't exchange anything with the surrounding world. And the reason for that is that if the small system then takes something here, that has to be donated by the large system and vice versa. So anything that goes in here is taken from the thermostat. And so this is our world. This is the universe. The large system can be, of course, be divided in tons of different microstates. And we can think of each point here as an atom, but again, that's just how we're thinking about it. And if we pick the small system small enough, let's pick just one atom or something, so that the second I picked the small system here, this is so small that this kind of corresponds to one microstate only. So if I pick that system, and that's perfectly defined, and then that one has some small energy epsilon. The rest of the energy must be the total energy minus that epsilon, and that is in the thermostat. But of course, the thermostat contains way more than one particle. So the thermostats, if these two particles change place, that's not going to influence the small system. I can trade place between these two particles, etc. So in particular, when this thermostat is very large, there is going to be a gigantic number of microstates for the thermostat that corresponds to the case when we're observing the energy epsilon in the small system. Do you follow me there? And the hard part here is, of course, that we haven't really assumed anything yet. And the point here is that if we can let's just call that something. We can call that M for macro states, large M. If that is the number of microstates that corresponds to the macro state when we're observing the small system here, that is kind of a function of the energy. And the probability of observing the case in this one, we have exactly epsilon there. Well, the more different ways the thermostat can be arranged, the more likely it is to observe that. That's not an entirely obvious result, but if you think about it a while, I think you will agree. If every microstate in the thermostat is completely identical, and we are asking you how likely is it to observe this small state in the epsilon state, the more microstates that corresponds to having epsilon there, the more likely it is to observe it that way, right? There's going to be a proportionality there. And then we just throw in our definition. So the only thing we have defined now, we've said that what is the energy, we've said that the energy is conserved. We're asking how likely is it to have epsilon there. And then we introduce the definition that that's the number of microstates. And then we've already said, or you can say that we define it again, that the entropy of that system, we just say that that's a proportionality factor multiplied by the logarithm of that number of states. The only reason, you might think that this is Boltzmann's constant, but it's not. Actually it is, but this is just a proportionality constant. Because we like to give this S term the units of joule per Kelvin, energy per temperature. So for now, this could be absolutely anything. So what we've essentially done is that we've divided the system into all these microstates of the large systems. We've divided them into different classes where each class corresponds to this small system being in exactly one state corresponding to epsilon. And this is something that you will likely read up in the book too. I would be astonished if you got this the first time. This is just a completely arbitrary constant. And now we're going to get a little bit more complicated, but this is I think this is the most advanced math we'll do. So entropy, for now this entropy is just a definition. And this is not more complicated than the definition. What I say here is just that S equals a constant times the logarithm of the number of microstates. The reason why this looks a bit more complicated is that I've stressed that it's for the thermostat, and I've said that this is a function of how much energy we have in the thermostat. But again, all this stuff is just eye candy, really. All this is saying is S equals K multiplied by the logarithm of the number of states, microstates. And then you're kind of screwed. How do you get further from that? Try not to look at it. Don't look at your notes. It's much better that you follow this, because this is something very typical in physics. So what you do in physics all the time is that you're looking at one state, and then you want to understand what happens around the state. Because if you're just looking at one state, you're looking at that state but nothing else. But the second you want to look at a process or something, you typically want to look at the surrounding. So what I've done here is that the state here is kind of capital E, and then we're looking at something small that's changing around it, the epsilon here. And the way you normally do in physics, if you're looking at a small variation, you do a series expansion. You remember that from calculus. If we take an arbitrary function, completely arbitrary function, the absolutely easiest approximation of a function at any point, that would be its value, right? If you want to start looking at how a function varies around the value, you would say that you have the f is approximately equal to the value in that point plus delta x times the derivative, right? Delta x or something. So then you're looking at both the value and the derivative. You can add the second derivative, the third derivative, and everything. You can go as far as you want. And if you have an infinite number of terms here, you could describe the entire function. And for most physicists, the infinity is usually 1, occasionally 2 here. So that you only use 1, 2, or occasionally 3 terms here. So I'm going to do a series expansion. And this is let me throw up the equation first. I think you think that this looks complicated, right? Is this completely obvious to all of you? Good! This is much easier than it looks like. So what I'm saying here really is that a completely arbitrary function here and how that varies around some point, that is just equal to, first we have the value in that point itself. That's the function value. And this should actually be an approximate equal sign here, not exactly. And then we have, actually, this should be, it's correct that it's a minus there, but you can think of this plus the delta x, the small variation around that point, multiplied by the derivative, right? And that is the derivative, because this is a function of an energy. But in this case, there is a minus sign before that change, so that minus sign moves in there too. So all I'm saying here is that the way the entropy changes around a value is the value of the entropy in that value, and then the deviation multiplied by the derivative. And all what this means is that this vertical line here means that I take that derivative at a constant value of the energy. So I put in the value of the energy as E here. So friend of order would then say, why do I stop after the first order term here? Why don't I have a second derivative or a third derivative or a fourth or a 50/11th derivative? This is going to be pretty bad because I kept saying at the start of this lecture that I would prove this and this is universal, and then I keep doing this horrible approximations. If this is an approximation, statistical mechanics is not exact. So there's an easy and a hard way to judge that. First, what is the value of epsilon compared to E?
Very small.
Yes. You could even say infinitesimally small, right? Because the whole point, the thermostat is something that is large enough. And large enough could in principle be the universe, while epsilon is very small. However, that is still an approximation. Just because something is small doesn't mean that the next term is 0. That just means that it's small. And you can think of that in a slightly different way. If you think of the system that I showed you, how does the entropy S vary with the number of particles or the size of the system?
More particles, more energy.
Yes, so to first approximation, it's proportional to the number of particles, right? So this term is going to be proportional to the number of particles. How does the energy vary with the number of particles? Again, to the first approximation.
The same.
Yes. So you take something that's proportional to the number of particles divided by something that's proportional to the number of particles. The first approximation, this term is going to be, yes, it's not proportional to the number of particles. The next term, the second order term, then you would have d2s dE2. So then you would have something proportional to the number of particles divided by the square of the number of particles. And for a system that's large enough, that's going to go to 0. So any higher order term will go to 0 as it's not just going to go, it's not just going to be small. If the system is large enough, it will go to 0. And that's why I actually can have an equal sign here, if the system is large enough.
So does that mean we only care about this when the systems are large?
Yes. And again, the whole point of statistical mechanics is that that's the statistical part of it. Statistical mechanics describes systems that are so large that we need to study average properties rather than individual properties. The cool thing here is that, remember, we still haven't really assumed anything about the system, but suddenly we can start saying that how things change, what are the proportionality constants here. There's going to be something that's proportional to our small energy here and everything. And this is the hard part about physics, but also the beautiful part. You can learn a lot of things by some very mild and simple assumptions. So for instance, the thing here we said about the magnitudes of these terms and everything, that's going to be true for any system. We haven't assumed anything about the system yet. And then you just throw up these things. This, I realize, is the hard part. Suddenly, I think the book 2 suddenly says, you're going to solve for m. That's not at all obvious. Why would we solve for m here?
Because it's going to tell us something about entropy.
Almost. You know what? I'll get back one slide. Remember what I said, that the probability of observing the system in this state is proportional to m, right? And this, of course, what we want to get to eventually. How likely is it that this system is in this particular state? And that's why, if that is described by m, of course, it's m that we want to get. And we made this definition that the entropy S equals a constant times the logarithm of m. This, I think, is typically something that if you didn't know what you were going to do, I would do a mistake here. And then you would need to go back and realize, wait a second, what was it really that I was after? If you don't know what you're after, it's very hard to derive it. But if you ping pong back and say, wait a second, I was interested in observing how likely the system, what could that likelihood correspond to? It's m. So let's jump back to here. So if we now have these expressions that's a function of the entropy. So we can use this equation again backwards and try to get m from it. And again, this is trivial. I'm just taking the exponential of both sides here. So that m equals the exponential of this entropy divided by the constant. Exactly the same thing as we have up there, formulated in a slightly different way. But now we also expanded how this entropy varies around this state, right? So now we can take this definition and put in there and see what happens.
Is it still m therm?
Yes, sorry, this is m therm. My bad. I ran out of space there. And if we take that entire expression, so that's a sum, or actually a difference in this case. That difference up in the exponential, an exponential of a minus b, or an exponential of a plus b is an exponential of a multiplied by an exponential of b, exponential loss. And then the minus sign here will follow us, so that this is an exponential of that term multiplied by an exponential of that term, including the minus sign. And then I just compressed that here to get it to fit on one line. And now we are actually starting to find some really interesting things. How does that first term depend? Remember that we were interested in our small system, the one with energy epsilon, right? How does epsilon come in the first term here?
It's not
Right, so what would you call the first term?
infinite.
For all intents, it's just a constant, right? We don't care what it is. You could call that C. Because at some point, we don't really care about the number of microstates. It's just that the number of microstates is proportional to something. And if you care about proportionalities, it's just a completely arbitrary constant. So in one way, we just approximated away the entire first term here. So that the number of microstates in the thermostat is proportional. Well, it's a constant multiplied by the exponential of minus the energy. And then we have something complicated in here. This derivative of the entropy divided by a constant. Sorry, derivative of the entropy with respect to energy divided by a constant. That is not obvious. But we can actually say something here. The number of microstates is somehow proportional to an exponential raised to the minus of the energy. So when the energy of the small system changes, it's going to reduce the number of available microstates exponentially, right? And then there are some constants that we haven't really looked into yet. And this is completely arbitrary. It's true for any system. We haven't assumed anything about the system. This is independent of epsilon. And that term is actually independent of epsilon too. So it's only in that small term where epsilon, the energy of the small system, actually enters.
It's pretty much the Boltzmann.
Of course. But that's what we're showing now. So this is, we're not there quite yet, but this is the Boltzmann. We just proven that the Boltzmann distribution is true for any system. We haven't even started to talk about Newton's laws or anything. And this is by far the hardest part with thermodynamics and statistical mechanics, that if you want to prove that things are universal, by definition, you can't assume anything. But the beauty of it is that this does not rely on any observation. This does not rely on the fact that, say, general relativity is true. And so the amazing thing with these things is that it's just based on observations and mathematics. general relativity might, well, you could argue that general relativity might not be true because you can't really combine it with quantum mechanics. These things will never be proven untrue because it's not based on observation. So what the book then gets to, and this is what I already hinted, the reason why we're solving for m is that the probability of observing this small part of the system in the state epsilon is proportional to the number of microstates of the entire world, the large system, that corresponds to it. So this probability is proportional to the number of microstates in the thermostat still, which in turn is proportional to, the beauty with these proportional signs is we can forget about this constant, or you could have an equal sign and a constant, of an exponential where the argument is minus the energy in the system with some large constants in there. And this, of course, is the Boltzmann distribution. And these constants, we don't really know more about them. So these are going to be important properties of nature. So one of them, this ds, how the entropy changes relative to energy. This is a constant, which I, in principle, could call T. The only problem is that that would then be the inverse of what you normally think of as temperature. So that the way we've defined these temperature scales and everything, the Celsius or the Fahrenheit scale were completely phenomenological. And then it turns out that if we now want to define an absolute temperature that behaves the same way you think of temperature, we should invert it. Otherwise, we should have a temperature that could go to infinity at 0 Kelvin, and then it would go to 0 at infinity. It would just confuse you. So it's just, you could argue that this is a mistake we did when we first introduced temperature phenomenologically hundreds of years ago. And it's way easier to fix that. So that's why we call it 1 over T, but this is just a proportionality constant. And this other small constant, kappa there, that is of course equal to your friend Boltzmann's constant. Why do we have the Boltzmann constant there? Because it's just really one constant divided by another constant.
It's just to give us the units that we want.
Exactly. So if we had started from scratch today and derived temperature, we would have measured temperature in units of Boltzmann's constant. So the only reason to have Boltzmann's constant is that we're used to thinking of temperature in terms of, well, this arbitrary temperature unit, Kelvin or Fahrenheit, well, Kelvin if it's absolute temperature. And to avoid screwing that up, we introduced this constant. But this, again, is really a historical shortcoming that we didn't know of thermodynamics when we didn't. Either you could argue that we didn't know about it when people first started talking about temperature, and when Kelvin, for instance, introduced absolute temperature and everything, it was simply easier to keep it compatible. So that today we would likely have some temperature called X that would be 1 over temperature and measured in units of Boltzmann's constant. And the gas constant is, of course, equivalent to that. That's just the only difference between gas and Boltzmann is whether we measure things per particle or per mole of particles. And in principle, that is the Boltzmann distribution. We just don't call it the Boltzmann distribution yet. The probability of observing a system is proportional to E, the exponential raised to the power of minus the energy multiplied by some proportionality constants, which we're going to call divided by KT. So the more you raise, the more the energy of our small system goes up, we reduce that number of states exponentially. You can actually show that. The book, that is a small exercise. I'll show you just for fun. If we look at how likely is it for the system to move to, say, KT, higher energy. KT was rather small. Do you remember how much was KT again? 0.6 what? Yes. The units are important. So that's a small energy by all intents and purposes. And if we assume what is the likelihood of observing the system is something that has changed there. In this case, we increase the energy of the large system. Well, we know what the definition of those microstates is. That's just the entropy. And then we can take this term and put in the series expansion again. I'm not going to go through the math for you. And that turns out we have this S term, and then we have t divided by t and k divided by k, that's 1. So this really corresponds to the logarithm of the number of microstates plus 1. Now what that means, for every kT you increase the temperature, there are roughly a factor 3 more microstates. You can go through the math if you want to. It's not difficult. Why do I show you that? Well, this is related to the fact why this kT is such a fundamental constant. So the second you go up 2 kT, if you raise a barrier by a factor 2 kT, it's roughly e squared, so almost a factor of 10. So by the time you're at 4 kT, you've reduced the probability by a factor of 100, right? And this is why things that are significantly larger than kT, the probability goes down extremely quickly. And conversely, of course, when barriers or something are significantly smaller than kT, the probability that something will happen essentially goes to 1. And this is why, and again, this is why the reason why this is such a, call it characteristic energy scale or something at room, not just at room temperature, but for systems in general. Sorry. So again, something in biology, a reaction where the barrier is much lower than kT will virtually always happen. And if a reaction is much higher than kT, it will never happen. And this is no longer just based on hand waving. You've proved that here. The point of this is that we know just a little bit more now. I'm going to go through a couple of more slides, and then I think we'll talk about this after the break. We've shown that the Boltzmann distribution is true in general. We have introduced concept of the entropy as a function of the energy. As the energy goes up, as the energy varies, the number of microstates goes up by a factor of 3 per kT. And again, the number of microstates, that is directly proportional to the entropy. The entropy is the logarithm of the number of microstates. So we can start to draw a curve where then there are a bunch of curves like this in the book. They're not entirely natural, but I think if the entropy, by definition, is a function of the number of microstates, and the number of microstates in turn is a function of energy, we can certainly draw a plot where the entropy is a function of the energy, right? Exactly how that curve will look, we don't care about right now, but it's some sort of curve that describes different ways where the system can be as a function at different energies. And understanding this conceptually is not entirely easy. This derivative that entered in the exponential that corresponds to 1 over the temperature, that is literally the slope of the curve. So this slope is 1 over temperature. And here we come into this point that you talked about the size of the system. We can really only define this if between these two, over a small energy range, if there are so many particles in the system that I can define this derivative, right? Because if there are hardly any particles or anything, these are going to be noisy, the number of states. So defining this as continuum properties of the curve, that requires the system to be very, very large. So I can really only define this slope when I have enough particle that I have a smooth curve. If the curve is completely random and everything, there isn't really any slope here. And this means that the whole concept of temperature, I can really only define temperature when you're dealing with things at equilibrium and many particles. I'll come back to that in a second. It is, right? Well, you can certainly define, you can define a microscopic temperature, but you can't necessarily measure a temperature. I'll come back to that in a sec. Let's see. Yes, I'll come back to that in a second, but just remember that the temperatures corresponds to these slopes of the curves, or 1 over the slopes of the curves. This might seem like more heavy mathematics, but the point here is that I'm going to show you how this is useful. If you now design a completely arbitrary state, I or whatever, you could say that the probability of being in that state, we typically use W there for weight. The weight to be in that state, for instance, as a function of temperature and energy or something, for state I, that will correspond to the exponential of minus the energy of state divided by these constants we already had. And in principle, if I don't have the denominator there, I should have a proportional sign here. But proportional signs are bad because, as you remember these labs, you can't calculate a proportional sign. If you're going to calculate something exactly, you need to know what is the constant too. And if you talk about probabilities, normally in nature, the probability of all things should sum up so the total probability is 1, right? You are in one state. We don't know which state, but if you sum all states, the probability should be 1. So there will, by definition, have to be some sort of normalization factor here that is the sum over all such states. And that's actually, it's very simple. I just said that. We sum it over all states. So that factor is the sum over all states I, and then I have exactly the same expression.
This doesn't really follow from the previous derivation, does it? It's just something you add into.
So the only reason I add in, rather than saying that the probability of observing something is proportional to, I want to be able to say exactly what is the probability. And then to get rid of that proportionality sign, I have to divide by the sum. And I think you did this in the labs, but you didn't think of it this way. My point here, there are two. This is one of the deepest results of statistical mechanics, but it's also a very obvious result. All of you could do this. You're just normalizing probabilities over a number of states so that the sum sums to 1. So mathematically and, say, statistically, it's completely trivial. The cool thing is that this is exactly what you asked about regarding energy landscapes before. This is the sum over every single possible state of the system. Every single possible microstate or macrostate, depending how you see it. Macrostate in this case. Do you think this is easy or hard to calculate? It was easy in your lab when you had 3 states. When you have 10 to the power of 25 states, it's impossible to calculate. So this is the sad and beautiful part. This tells you everything about the world if you have an infinite amount of time and infinite compute capability. If you have a small system, we can calculate this exactly. If you have a small system, on the other hand, what is the point of using statistical mechanics? Then you could just use a computer and calculate all the motions of the particles exactly. The beauty of this, we need statistical mechanics when our systems are so large and so complicated that in practice we can't solve this. We can't. And then it's time to give up and close this course and go home, right? This is our friend, the partition function. And the cool thing is that, let's just assume for a second that we know what the partition function is. That our system is easy enough that we could calculate it with a large supercomputer. We know what the probability is of being in every state. So I can calculate everything. The energy of my system is just the sum over every state. What is the probability of being in that state multiplied by the energy of that state? Pure statistics. Sum it up. Super trivial. Entropy, same way. The total entropy of the system is just the sum over all states. What is the probability of being in that state multiplied by the entropy in that state? And I'm actually going to help you a bit because I have a derivation of this. I will take you through that relatively quickly because that's not... What is SI here? What is the entropy of a small state? It's not entirely trivial. The book goes through this in some detail. So if you bear with me for just 5 minutes, I will take you through how we can calculate this. And it's going to turn out that this is a simple logarithm of the weight of each state. But this is kind of a parenthesis. My point here is that if we know the partition function so that we know these weights, you can kind of calculate everything about your system. But to be able to calculate that, I can't have something that I don't know what it is. So we're going to need to be able to calculate what SI in each microstate is. The way that both the book and I kind of like to derive this is that, so this is the beginning of the parenthesis. If you have a large number of n different systems that can be distributed in smaller systems, system 1, 2, 3, etc., all the way up to j. And there are some weights here, weight 1, 2, 3, etc., all the way up to j. 1, 2, 3, etc., all the way up to j. 1, 2, 3, etc., all the way up to j. 1, 2, 3, etc., all the way up to j. 1, 2, 3, etc., all the way up to j. 1, 2, 3, etc., all the way up to j. 1, 2, 3, etc., all the way up to j. 1, 2, 3, etc., all the way up to j. 1, 2, 3, etc., all the way up to j. 1, 2, 3, etc., all the way up to j. 1, 2, 3, etc., all the way up to j. 1, 2, 3, etc., all the way up to j. 1, 2, 3, etc., all the way up to j. 1, 2, 3, etc., all the way up to j. 1, 2, 3, etc., all the way up to j. 1, 2, 3, etc., all the way up to j. 1, 2, 3, etc., all the way up to j. 1, 2, 3, etc., all the way up to j. 1, 2, 3, etc., all the way up to j. 1, 2, 3, etc., all the way the number of systems that you have in each state corresponds to the weight of that multiplied by the total n here. And the sum of all those weights must be 1, too. Then you have to go into mathematical statistics and start calculating. So how many different ways are there to sort these balls or dices or something in these different systems? And it turns out that this leads to a long description where you start looking at probabilities. Oh, sorry, wrong order here. So if you start picking n1 systems for the smallest one, that corresponds to, well, the first one we can pick from capital N, the second we can keep from capital N minus 1, etc. And then you need to do this math correctly, and you need to keep the tongue right in your mouth. If you want to go through this in detail, follow the book. I've had some extra terms in there. We use a Stirling formula to get the second expression, and then you just keep doing math. And after a while, you can show that this expression is equal to 1 divided by all these weights raised to the same weight multiplied with each other, raised to the power of n. The only thing you're using here is mathematical statistics, really. But this is not a course of mathematical statistics, so I don't really care about it. For a single system, the total entropy in the system turns out to be 1 divided by all these weights raised to itself multiplied with each other. And in that case, the entropy, which is the logarithm of the number of ways we can distribute that, turns out to be the sum over the weight multiplied by the logarithm of 1 over the weight. This is by no means obvious. The point is, and the reason why I'm even showing this derivation is just trust me, this is just a matter of statistics. You don't assume anything about the system, you don't assume anything of the world. But in the end, the entropy of a state just depends on the weight of the state and the logarithm of the weight of the state. So this really only depends on how probable a state is. What does that mean? Well, assuming that you have 1,000 states, and if you have one of those states that's extremely probable, then that one is going to be high. But it's going to be really low for all the other 999 ones. And if W is very high, this is a small number, and then the logarithm becomes small. So if you have one state where you have almost everything, you're going to have a low value for this. But if you had all your 1,000 states had almost exactly the same weight, 1,000, then both of the terms are going to be relatively high. So if you have lots of states where it's roughly equally probable to be, then this is going to be high. But if you have one state where it's much more likely to be, it's going to be low. So this also agrees naturally with our concept of disorder or anything. And if you're doing, I'm not sure how far you got into bioinformatics, but it actually turns out that you can define something called the Shannon entropy in informatics. And it's actually exactly the same way. Just the probability of something has nothing to do with physics. You can define this in computer science too. Exactly the same way. End of parenthesis. Remember that I said that the energy in a state is just the sum over the weight of each state multiplied by the energy. Sorry, the total energy is the sum of the energy in each state multiplied by the weight. And in exactly the same way, the total entropy in a system is the constant, which we can put outside of the sum, and then this sum of the definition of the entropy in each substate. Sorry? Let's try that in a second. But my point here is that if you know the partition function, you know what Wi is. We know what this is, and we know what that is. If we know the partition function, we can calculate these exact numerically. And you might think that I or the book made a typo here. I'll get it. What you really want to know is the free energy. Why do you want to know the free energy? The free energy, exactly. The free energy determines everything what happens in chemistry, right? And this is now how we're getting back to chemistry. If the free energy is, if a change in free energy leads to a reduction in free energy, then that's a process that's going to happen. If the free energy goes up, that's a process that's not going to happen. If I know the free energy of every single point in my energy landscape, as you asked about, then I know where in the energy landscape I'm going to be. Then I could predict everything. I could instantly predict where a protein is going to be. I can predict if a mutation is going to stabilize a protein. I can predict whether a protein will fold. I can predict literally about any chemical reaction. And every single thing you observe in the lab is a product related to the free energy. So if I know this, this is our holy grail. We know everything about chemistry. But we just know E and we know S. So this is, the first term here is going to be, well, you see the W here occurs in both those parts, so let's break out the W. And then we have an epsilon j minus T, and it's just so cumbersome to keep working off the logarithm of 1 over something. And if you remember your logarithm laws, I can take that that is minus the logarithm of W instead. So that minus comes from removing the 1 over W there. Don't worry about the exact details of the equation. The whole point is I've just taken those two expressions and put it in that form. The point here is that if you know Z, you can calculate F exactly for any state the system is in. You can instantly say what is the free energy in, and again, this is an absolute free energy. In kilojoules per mole, the likelihood of having this particular transition state or anything of your protein or a molecule. But what is the point of this derivation if we can't determine that? Well, there is a reason why I bet why people have fought so much with statistical mechanics, because this is complicated. And it's also, historically, it's very much something you do with paper and pen. Historically, you might get up to 10 particles or something, 10 states doing it manually, roughly the size of things you did at the lab, right? Anything more complicated than that, you won't be able to handle. But there is a difference between today and 100 years ago, is that we have computers. So if you look at this, again, this is a sum where we have some complicated expression, but we also have this weight here. So if you have a particular state and the weight is 0.2, is that an important state? Well, yeah, kind of. It contributes 20% of everything we're seeing, right? If this weight is 10 to the minus 39, do you think it's very important to have that state? So the point is that some states, all states are not created equal here. Some states might be important to consider, while other states might not be important to consider. So while yes, if you do know Z exactly, you can calculate F exactly, but conversely, if you know Z approximatively, you can calculate free energies approximately. Well, the whole point, this is essentially what you end up doing in a computer simulation, right? That if we can sample, essentially what this is, if we can sample all the states that have high weights, the states that have high weights really corresponds to the ones with low free energy. The likelihood that a protein spontaneously would go through a fusion reaction and turn into a nuclear reactor, well, technically it can happen. It's not probability 0, it's just probability 10 to the minus 5,000 or something. I think for all intents and purposes, the likelihood that protein spontaneously starts to go under fusion, it's kind of 0. But now we start to approximate our partition function. But the point is that if I can sample enough of the states that are relevant, low free energy, I can calculate F, compare F between two states. And in particular, that's what we did very early on in the course. If I only care about two states, I really only need to sample those two states, right? To determine how good they are relative to each other. The rest of the world doesn't matter. So what this means is that the faster our computers have gotten, the better we can calculate properties for systems. Not just with one particle, not just with 10, but gradually going to 1,000, 10,000, 100,000. And many of these large computer simulations that we do today is simply that computers are so fast that we can sample systems that have hundreds of thousands of degrees of freedom. There is no way we sample them exhaustively. but we sample them well enough over the degrees of freedom that are relevant that you actually can start making conclusions. And essentially what we're doing, we're starting to approximate this partition function. This leads to something else that's very important. We should take a break here in a couple of minutes. You might think in a simulation that you're simulating nature. If I take a protein, for instance, and start to put that in a computer and push the button, I can simulate how it moves. You saw the movies, 2 weeks ago, that I showed you these proteins moving. That is not what a simulation is. That's how a simulation looks. It might look absolutely beautiful that you're having velocities and everything. But what all simulations do are really that we're sampling things. We're sampling as many states as possible and calculating how likely these states are. Eventually it's going to turn out that it's really advantageous to try to do that by approximating its motions, but you can't simulate a motion of a protein. You don't know it exactly. But we can use it to sample states. And this is also the reason why in all these labs, why you spend all this time with this dirty toy systems, right? It's much easier to understand this on the simple toy systems, and then gradually when we understand those, we're going to move back to the real systems. The danger with starting with the real systems is that you think that you can do an absolute simulation of nature. You can't do that. I think this is I know that there was a lot of mathematics here. This is a great place to take a break. What I'm going to do after the break is that, you remember that curve that I drew up, how the entropy varies as a function of the energy? We can actually use that to start drawing some conclusions about what will happen for different systems and how do systems behave under different circumstances. And then we'll see, depending on how much time that takes, I might have time to start applying this a little bit to alpha helices, because many of these things might probably be easier to grasp when you see it applied. But there's lots of deep mathematics here, so it's definitely worth reflecting a bit about that. It's 10:25 now. Should we take our 15 minutes or so and meet here at 10 to 11? So the main conclusion from last night, if we know simulations in general, they approximate the partition function by sampling the system. And the beauty here is that only the systems that are relatively likely to happen will be important. So if you think of this in this energy landscape, those very extreme peaks in red, the ones that are extremely unfavorable, if you just simulate a system, you're never going to visit that point. But the whole idea is that nature doesn't really visit it either. So it's not really, if you determine, say, the average conformation of a protein or some average observable, that's not really going to be particularly influenced of properties in these extremely unfavorable systems. And that's essentially why simulations and everything will work. We are pretty good at approximating the partition function with fast computers. What I'm going to talk a little bit about now is plots, that where we plot this entropy as a function of the energy. And this might seem bad, but remember what I said in the beginning. This allows us to start defining what we mean by these things as instability versus stability of a system. So in general, the only thing that we've said is that the entropy is a function of the number of microstates, and the number of microstates in general was a function of the energy in a system, right? That's what we showed the first half of today. And that means that in general, the entropy is a function of the energy. That means given a particular energy, there will always be one value for the entropy. And then I also said that in general, the slope of this curve is 1 over the temperature. But if you now, for some curves like this one's, that slope will be negative. So both of these curves will correspond to negative temperature. Can you have negative temperature? Sorry? So this comes down, at the end of the day, this comes down to definitions, right? I would actually argue you can have negative temperatures. Now, this is even an absolute temperature. You can have negative absolute temperatures, but not at equilibrium. So what this means that the point is that this blue line would technically be a positive state, but it would instantly want to move away from it, so that it's completely impossible to define this as temperature. But if you have something like a gas during the expansion of a gas during a split second or something, when the system has not yet reached equilibrium, technically you could imagine a system where as the energy goes up, the entropy goes down. Because that's what's happened in both these cases. You get more energy and anyway the entropy goes down. But that would be that if you're somewhat during a process where things are freezing, but for whatever reason the energy goes up a little bit, you will virtually never ever be able to observe anything like this because the times over which this happens would be infinitesimally small. So macroscopically, under equilibrium, you can never observe a system under conditions like this. Technically, physically, the way you just define a temperature, it's formally possible. And there are some fun, I used to have a paper on this, but it's just physics, it's not that important. There are a couple of cases where people argue they've been able to measure things that correspond to a negative temperature, absolute temperature even. What does this correspond to? Well, this is a system where as the energy goes up, the entropy goes up too, so it's kind of more natural. But this is a concave region. I can definitely define what the derivative is here, and this derivative will correspond to a finite positive temperature. But along this line, I know what the energy here is constant, and this line corresponds to E minus Ts, where the temperature is constant along it. So this black line here, the tangent, that would correspond to a given free energy, right? E minus Ts, that's why it's a line. But the point here is that all points further up here in the curve has lower free energy, and all points further down there have higher free energy. So every single possible state along this blue curve, except my point, has lower free energy. So that point is the highest possible free energy the system can have. That is physically possible, but that corresponds to the system balancing on the edge of a knife. It's a local point where the derivative is 0, so we're not going to have a force to one or the other direction. But if you make an infinitesimally large change either to the left or the right, we're going to fall down on one side of the knife's edge. So that corresponds to a system that's balancing at the peak of a transition state or something. It's not impossible, but you're never going to observe it there, because it will fall down on one side or the other. And conversely, a system that is stable always corresponds to a region that's convex here. So this is the extreme opposite. The blue curve is again the entropy as a function of energy. But in this case, the black curve here where we are, this is the lowest free energy we can have along the blue curve. Anything that's even lower would be up here. I can't reach that on the blue curve. And all other points below this black line has higher free energy. So this is a system that for this particular energy, it has found the absolutely lowest free energy it can be in. So in practice, all interesting regions that we can observe at equilibrium are going to be convex.
Isn't this a really odd way of representing this? Like really non-intuitive?
It is. No, I agree. It's very much not. Don't try to think of what this really means in terms of the system. Again, entropy, this is just something we have defined, right? My only point with this, don't try to understand what this means. My only point here is that we can define what's possible along these blue curves. Don't try to think in terms of what happens here or anything. These are pure mathematical definitions. The point of this is this slide. If we now have a larger curve here, and if the energy changes here, now we can start to look at multiple points along this curve, and then you have different temperatures. And in this case, this is a higher slope, which means that the temperature is lower, and as we go up here, the temperature goes up. And we can draw that in a different way. You can say, how does the energy vary as a function of temperature? And this is way more natural. This is how you would think about it. So as the temperature goes up here, the energy gradually goes up. And what this corresponds to is something that can happen smoothly. You can be there, 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 there. There's any point you pick along this blue curve is going to be a perfectly nice point where you're going to be happy to be. If you think of any process or something that changes, what does this correspond to? Something that can change this way, smoothly and nicely. Yes. So if you have water at, say, 10 degrees centigrade and go all the way up to 99, nothing dramatic happens. You can stop at any point you want. It's fully reversible. And what you're going to see is that there's going to be a distributions in energies or something in your particles. And as you go up, this distribution will gradually move. There is nothing special happening. It's kind of boring. But it should be boring. But the point is that this blue curve can of course look absolutely any way we want. There's nothing to say that the blue curve will always look like this. And in particular, let's assume that we start to have a blue curve that's starting to have some small depressions that goes up and down a bit, so at least the second derivative is varying. So here we have one temperature here. You have another temperature up here. But right in between here, there's a concave region. Remember what I said about the concave region? That's this local maximum where we don't really want to be. So we can go smoothly all the way up to energy 1 here, and then it's going to be bad. We're going to be unstable in this region, and then we can be at energy 2, and then we're happy and stable again. And there is some sort of gap between these two. That corresponds to a gap in energy, but also some sort of, you could imagine there is some sort of characteristic temperature here that corresponds to the slope between these 2 points. That's going to be between these 2 temperatures. In principle, you can do the same thing here. We can say that we can plot how the energy varies as a function of temperature, and this curve is going to be roughly the same. But now there's going to be some sort of range, both in energy and temperature here, where we are not stable. In this region, we don't want to be, because that corresponds to the bad part here. And this really means that as we're starting to heat the system, we have one state here, and as we go up, we don't move between them. So the particles that move away from this state, they have to move all the way over to the second state directly. You can't be here. You don't want to be here. This is one side of the knife, and that's the other side of the knife, say. And this is true for any system. We haven't assumed anything. It's just the way entropy and things vary. So what does this correspond to? You think? You had a good example, water.
Phase change?
So this would be ice, right? And then something happens, and then you have liquid water. So this is a phase transition. And you might think that this is that you can have both and ice at the same time, you might think, but I would actually say you can't. I'll show you why in a second. But there is some friend of water would again say that there is something wrong here. I keep talking about this temperature range and everything. Have you ever heard about the temperature range where ice melts? So the book goes into some detail. You can actually calculate this. You don't need anything more than these equations. But in particular, well, given what I did before the break, I kind of assumed that you wouldn't like me to go spend another 5 slides on equations. The point is that this evaluates to a very simple expression. You can approximate this range in temperature is roughly 4 times the Boltzmann's constant times this temperature that roughly the temperature where we're having the transition happen, divided by the difference in energies. And then it's just a matter of doing the mathematics here. You can say for ice melting to water, this temperature is roughly what?
So degrees?
Yes, 273 Kelvin, right? We know what the Boltzmann's constant is. The energy here, well, that depends on the size of the system, right? But if you're looking at something typical like a kilo of water, the phase transition energy is roughly 50 kilocalories. Not per mole, but 50 kilocalories, period. That's a very large energy compared to Boltzmann's constant, because you still have Boltzmann's constant here. So it's technically true. There is a range over which ice melts to water, and that's roughly 10 to the minus 24 Kelvin, which for all intents and purposes is 0, right? That macroscopically in the lab, you feel like water melts exactly at 0 Kelvin. So what's the point of going through that if this is so small that in practice this is just one point? That it goes here and then say boom, and then you're at a different energy. Well, that's because you're looking at a large macroscopic block that is 1 entire kilo of ice. If this is rather a protein, again, we can use 273 Kelvin there too, or 300 if you want to do it in the lab. But the point is that the energy difference for one protein, that's the energy difference for one protein molecule. And then you're maybe talking still about 50 kilocalories, but per mole. And that's a difference of 6 times 10 to the power of 23, right? And suddenly you're talking about an energy range that might be 10 Kelvin or something. So for small molecules, these are finite regions. A protein will have some sort of phase transition that happens over a finite region. And I've already spilled a bit of the beans here that protein folding corresponds to phase transitions. But they're kind of different from the phase transitions that you would see macroscopically in ice and everything because it's such a small system. And in principle, I could stop here, but this corresponds to what you say is a first order phase transition in physics. And if I said first order, there must be a second order, right? So I'm just going to tell you what the difference here. A first order phase transition is characterized that there is a fairly abrupt change in energy as a function of the temperature. This is, remember, this can be a very, very narrow region, and the energy starts to change significantly. And a second order phase transition is almost the same. Think of that as a second derivative. That just means that there is an abrupt change in the slope of the energy as a function of temperature. And then there are actually other types of phase transitions too. We're not going to go through the higher order phase transitions. They're not really relevant for the proteins we're looking at and everything. But there are lots of ways to study this in physics if you're interested. And that actually it corresponds to jump in heat capacity. So you can measure that too. You know what the good news is? This is all the statistical physics you will ever need. But with this, we can now start to study way more interesting concepts. So that when you're looking at thermodynamics is kind of boring in a way because thermodynamics without statistical mechanics, that just looks at what happens at equilibrium. What happens if you have had an infinitely long time to relax. But there is nothing in what I've said here that actually assumes that we always must have equilibrium and everything. So we can start looking at how fast reactions happen, for instance, transition rates. Because all this really corresponds to different free energy barriers and how easy it is to move over them or not. And the neat thing with that is not whether you could argue that statistical mechanics and just look at the Boltzmann distribution, that just tells you if things will happen at some point infinitely far away in time. The difference with kinetics, we can say when things happen. There's a fundamental difference there in the energy landscape that you can think about. I'll come back to that in a slide or two. What this means is that if we have, in general, if you have some sort of reaction, and this can be any reaction, but think of, say, two small chemical molecules bonding or something. You typically say that 0 is the initial state and 1 is the end state. What would happen if you just had a downhill slope from 0 to 1? It would instantly go to 1, right? You couldn't even measure it. That this would only be limited by the diffusion of the particles. And again, if two particles are already close to each other, there again, it would happen instantly. You couldn't even measure it. So the reason why most processes or reactions are finite is that it's not just enough to go there, but to go there you somehow need to get over some barrier first. There are lots of reasons for this barrier. It might be that you have super low concentration so that it takes time just to diffuse and find each other. That's a typical entropic barrier, right? That you need to seek and sample all parts of the system until the molecules find each other. It might be that you need to bind the molecules in a sort of strange way, or that the molecule have to bind something else that's very unfavorable from an energy point of view. That would be an energy barrier. So that's the whole point. There is some sort of barrier in free energy, and exactly what that is, we don't really care. But if it doesn't happen instantly, there is some sort of barrier here. And you can of course imagine a general complicated chemical reaction might go through lots of these barriers. We'll come back to that in a second. You know everything to derive this yourselves. But I'll take you through it anyway. What is the likelihood? Sorry, I copied this from the book. There's a sharp sign there. There's an F sharp or something up there. What is the likelihood of being at the top of the barrier?
Not very likely.
No, but not very likely doesn't kind of, well, actually, I said that's wrong. That depends on the height of the barrier. If this is 0.1 kT, it might be very likely. So in general, the number of particles n sharp we have there, that's just the Boltzmann distribution, right? We can say that that's roughly the fraction of the particles we have up there compared to the number of particles we have down there. That's the Boltzmann distribution, e to the minus the difference in free energy divided by kT, right? The likelihood of being there compared to being down there. And then friend of order you can of course start to say, well, you should compare the number of particles n sharp to n minus n sharp and everything. But in general, if this barrier is reasonably high, it's going to be a very small fraction of the particles that are up here. So it's not, the particles that are up here won't really affect the particles in the zero state. So the probability of being up here is the original particles multiplied by the Boltzmann distribution. And if the delta F is high, this is going to be small. If delta F is small, this is going to be large. And then we need to approximate things a little bit. What happens when you're up here, the first approximation?
You go down instantly and to the right of the
Yes, and which side do you go down to?
actually both.
Yes, it's 50-50. So in principle, if we are up here, in a given time, the number of particles that falls down should somehow be proportional to the number of particles that are up here. And in principle, it's a factor of 2, but you know what, we're thinking about orders of magnitude, but let's forget about that factor of 2. Let's just assume that once we reach this energy, we somehow continue to 1. I'm well aware that I'm making a factor of 2 difference error here, but it doesn't really matter. And let's also assume that if I'm up here, the time it takes me to go down, that should somehow just be limited by diffusion or something, but it's not going to happen instantly. It will take, say, a femtosecond or a picosecond or something. So there's going to be some very short time here that corresponds to the process, some sort of characteristic time for the process. We don't know what that is, and if we don't know what something is, we'll just call it something, tau. So there is if we are at the top, the time it takes to go down is tau. And of course, we can say that our factor 2 is part of this. If it's only a constant, right? If it's a factor 2 difference, we can include that factor of 2 in that constant. But that means that in that time, tau, the number of particles that moved over was n sharp divided by n right, the fraction of particles that had come up to the top. So after the time tau, n sharp divided by n particles have moved over. So again, approximately the time for all particles to move over, well, that's going to be, if n was 100 and n sharp was 2, that was 2 divided by 2 of 100 particles. But that also means that it's going to be 100 divided by 2 such batches, right? If there are 2 particles in each batch, it's going to require 50 batches until all of them are over. Do you follow me there? So that the rough time for all of them to go over is roughly going to be the time for each step, and then the number of particles n divided by n sharp. And again, we're also, here we're kind of ignoring that some particles might go back in the other direction. We're just talking about orders of magnitude here. And if you're not happy with those orders of magnitude, you can put an arbitrary constant as part of tau. But what this means, we know n divided by n sharp. That's just the opposite of n sharp divided by n, right? So that just means remove the minus sign there. So the time it takes for particles to go over here is really the time it takes to go downhill once we are at the top, multiplied by an exponential raised to plus the energy barrier divided by kT. So what we're saying here is that this time for the reaction to happen is now proportional to an energy barrier with a plus sign. The higher that energy barrier is, the longer it's going to take you to go over. And this increases exponentially. And remember what I said before, when things happen or not, that's related to kT. If this one is significantly higher than kT, the time for this to happen is going to grow exponentially, and it's going to grow exponentially very quickly. And if delta F is much smaller than kT, well, this time is going to be so small that it would happen, all of that will happen instantly, essentially. So the amazing thing is that now we're moving over from things that are statically distributed until saying that when do things happen. Now, there's of course one horrible thing here. We have this tau, and I haven't told you what the tau is. In general, this still depends. You could apply this to, say, cars that are driven between Stockholm and Malmö. And in that case, 1 picosecond would be a pretty bad approximation of that time constant. But this is just about any system. And if you define a system, we can define what this time constant is. in general with chemical reactions, there is more than one way for things to happen. You can imagine that you might have a reaction that can happen with or without a catalyst, for instance. And then there's going to be two times. One slow time where it happens without the catalyst, and a fast time when it happens with the catalyst. Which one is going to happen? Well, in principle, you should then start calculating what is the probability of going over barrier 1, what is the probability of going over barrier 2. And the point is that, of course, if one barrier is much lower than another, all these weights will be dominated by the lowest barrier, right? So in general, if you have multiple pathways, the pathway with the lowest barrier is going to dominate the total time it takes.
But is it all or nothing, or will it always be kind of?
What do you think? If you have, that's actually a very good idea. So if you have a system that can happen, say, 3 different ways, which way happens? One of them has an energy barrier 1, another 10, and a third 100.
I think that they all kind of happen with proportional to the.
Exactly. This is actually a more important question than you think. For a long time, we used to think that protein folding only happened one way. But if there's one way we've seen from modern computer simulations, and these are still too slow for you to do them yourselves, but we've seen that in folding at home, for instance, which they're using distributed networks all over the world, that protein folding is not a matter of a protein folding one reaction pathway. You should rather think of this like a spider's web, that there are hundreds of different pathways. Some pathways are more dominant than others, but all of them can happen. And depending on how large and complicated the protein, for instance, is, you can have either that one pathway corresponds to 99%, or that the most dominant pathway is only 50%. It depends on the system. The problem, though, with that is that if you're going to work with that, you end up having to do the Boltzmann weighting of all these times and everything, and this is just tedious and complicated and everything. So when we determine when things happen, instead of saying that this transition takes 5, it's much easier to work with the reciprocal. And the reciprocal is these transition rates, and they're just 1 over the transition time. And the advantage of that describes how many particles cross per second, essentially. And if a transition is more likely to happen, the transition rate is going to be higher. So usually it makes much more sense to talk of things in terms of rates rather than transition times. The other nice things with the transition rates is that you can add them. So if you have one transition rate at 0.5, another one that's 0.2, and a third one that's 0.1, the total transition rate is going to be 5.3. So then you can sum up all these different pathways rather than doing the Boltzmann statistics. But they contain exactly the same information whether we talk about times or transition rates.
Can I ask something?
Sure.
Something I'm missing regarding tau. So you said tau is like the characteristic time of the process, like the fastest or the shortest time there is involved in the process.
Mm-hmm.
So like 1 per second for molecular reactions or something like that. But then why do you multiply by the quotient of the number of states? I don't know. So I get that.
No, so but that's a good question. But imagine that n is a mole, 6 to the power of 23, right? Would you consider that if you now measure this in the lab, what we measure there is, of course, has the reaction happened, right? And if 1 out of 6 times 10 to the power of 23 molecules have moved over, I think your answer would be no, the reaction has not happened yet. So after this time, for this, in principle, what I guess you might want to say 50% or something here. But again, we don't worry about those factors too. And you can fold those into because we don't know the exact value of this time anyway, right? So if you wanted to do this, I guess you could do this more accurate and say that you consider that the reaction has happened in half that time. Because that's when 50% of the molecule have moved over. So here I would rather say roughly as if all the molecules have moved over. The reason why I don't do that is that when 50% of the molecules have moved over, we should no longer compare n sharp to n, right? But we should compare n sharp to n divided by 2. It has just become so much more complicated, and in the end, the largest error you're going to make is a factor of 2. And in particular in chemistry, because of these exponentials, we're talking about orders of magnitude. Factors of 2 rarely matter. The other thing that will happen, as I already alluded to that, if you now have multiple of these barriers that are parallel, the lowest one will dominate. If you have a reaction that needs to go through multiple steps, it actually becomes pretty complicated. You can do the math, and if you have lots of steps that are roughly the same magnitude, it gets really complicated. But if you have multiple steps, let's say 1, 2, 5, and then suddenly one that's 25, and then 5, 2 again, the highest barrier will dominate there. So if you go through multiple steps, but one step has a significantly higher barrier, that one is going to dominate the waiting time. So if they are successive, if they happen to have after each other, you need to wait for the highest barrier. If they are parallel, that you can choose one or the other, you're going to go over the shortest barrier. And if you think about it, that probably makes sense, right?
When you go over multiple barriers, can you treat them sort of separately, or do you have?
So that's essentially what you need to do. So what you do here is that you start here, and then we apply exactly our normal mathematics to go from here to x.
Yeah.
However, the problem when you are in x, one option is to go forward to 1, but another option is to go backward from x to 0. That might not be so obvious here, but in particular in this right? So here we start with x here. The intermediate state here is actually worse. So when we are here, it's going to be better to go back than to go forward. So in this, and in general, if this is very bad, you're going to have a significant backflow of particles. And that's why at each intermediate state, you will have to account for the fact that you can both go backward and forward. But that, of course, also means that in one state, it's much more likely. You can assume that it's equilibrium before that transition, and there's equilibrium after that transition, and then it's only the highest peak that matters. And this depends. For a small protein, for instance, it's usually only one barrier. That is that they fold all or nothing. For a very large protein, such as a ribosome or something, they have to go through a ton of different steps, and that's usually why they take much longer to fold. My point for going through this is that this is way more applicable than you might think. So the idea is that we're going to try to apply this to secondary structure the last 30 minutes or so. And the simplest secondary structure we can imagine is the alpha helix. What you occasionally talk about is something called helix coil transitions or helix coil equilibrium. And that just means that I'm looking at a string of amino acids, be it 50 or 100 residues. And then you look how much of this string is alpha helix, how much of it is coil, that is without structure. And how would you measure that?
Hydrogen bond?
By what method? CD, yes. This is the reason why CD spectroscopy is, because suddenly, and this is more important than you think, suddenly you can use a super cheap machine that you can find in any lab, and it's so cheap that I can order 10 more if you need it. And we can use that to peek into the atomic detail of entropy and enthalpy, for instance, of proteins. We can look at beta sheets too. We'll wait there. And actually, the random coil will probably wait tomorrow. You are experts on the alpha helix now. So you already remember that each hydrogen bond goes from residue I to I plus 4, right? And this is kind of obvious, but so the first residue, well, so 1, 2, 3, nothing really happens. When we form the first the hydrogen bond from residue 0 to 4, this really locks 3 residues into place, right? Residue 1, 2, and 3. The first and last are a bit free to move, at least half free. Residue 4, on the other hand, when we form the next hydrogen bond here, we also look 2, 3, and 4 into place. So in general, n residues are stabilized by n minus 2 hydrogen bonds. It's just the math. So these 3 are stabilized by 1, and these 3 are stabilized by 1. But in principle, that's enough. Then we know how much we stabilize things by. In principle, we can write down the free energy. I bet you wouldn't. This is not entirely natural, but this is also physics. The free energy of any transition is the free energy of the product minus the free energy of the starting state, right? So going from the free energy difference of going from a coil to an alpha helix, that should just be the free energy of the alpha helix minus the free energy of the coil. And then let's just assume that we have n residues. There is one part here that's energy, and we know how many, the energy of one hydrogen bond, we have no idea what that is. Actually, you do, but only amateurs would say that a hydrogen bond is 5k cal. You're professionals now, so you're going to say that the energy bond is just call that FH bond. That's the free energy of this hydrogen bond.
Why do we change the F?
Why we use a lowercase f? And in this case, because this is the total for the chain, and here I'm thinking the energy of an individual hydrogen bond. The beauty is you could use x if you want to, as long as you define it, or z, or you can use the Greek or Cyrillic letters or something. That's the great thing with physics. And we know that for n residues, we have n minus 2 such hydrogen bonds. And right now, this seems, we haven't really learned anything. We've just said that this is the number of hydrogen bonds. But we've also taken those residues and forced them to be in a helix, because all our residues are in a helix, all the n residues. And there is some sort of entropy loss because they're no longer free. We have to force them to be in a helix. We have absolutely no idea what that is now, so we'll just use the letter S for it. And that S is really the loss of fixating one residue in a helix. And if we forget about the lower term there, this might seem, we don't really, well, at face this is not really obvious, but there is an n there. So we n multiplied by the hydrogen bonds and n multiplied by that term. And there is one term here that does not depend on n. So let's just for fun write it that way. So we have one term here that does not depend on the number of residues, and then a second term that depends on the number of residues, right? And we still don't know what these terms are numerically, but we can definitely say that the blue doesn't show very well here. This is the cost of starting the helix, because whether it's 1 or 5,000 residues, that's what you're going to pay. While the second cost here, this is the one that's proportional to the number of residues we have in the helix. Can you guess anything about, assuming that you have a small chain that does form alpha helix, can you say anything about these terms? And you can write this, that there's some sort of initiation cost and some sort of the number of residues times the elongation cost, and that's why I use those names, init and el. Happens to be my initials too. Can you say anything about the terms?
It has a low initiation.
Well, can you start saying something about the sign? So here's total delta F. What are the sign of those terms? Sorry, what's negative?
The initiation.
So what would happen if the initiation was negative? You would be on the downhill slope, right? Then it would instantly form alpha helices. So I would actually say that's wrong. This is kind of an open goal for somebody else to suggest another. Well, it could be 0 too, I guess. But if it's not negative, it might be positive. So you're going to pay. It's not good to form an alpha helix. And remember, the reason for this is what you're going to pay. If you were to put one residue or two residues in an alpha helical state, we haven't started to get those good hydrogen bonds stabilizing you yet, right? So initially, you're only paying. And this is why it's uphill, so there is some sort of energy barrier we need to get over. This is the energy barrier we need to get over. That term, on the other hand, what sign should that have if we'd like to form alpha helices? Negative, yeah. So that first we start to pay, but as we're growing this, eventually this goes down again, and if the helix is long enough, we're going to gain a lot of energy to form an alpha helix. But it will not form instantly, because we're not going to get over this barrier instantly. There is another way of formulating this, which is how people have usually done it in chemistry. And it's not as hard as you think. Exponential, and we have our delta F there, right? Just take that delta F and we expand that into initiation and elongation. But that delta F is a sum, and if it's a sum inside an exponential, that's a product of two exponentials, right? And that n we have there times the number of residues. Well, this is the cost of elongating one residue, but I'm allowed to take that n and move it out and raise the exponential to that as an exponent. It's exponential laws, you probably don't remember them, but it doesn't matter. So this entire expression, the exponential of the initiation energy, we can call sigma. And that second term, the exponential of the elongation per residue, remember the n is outside, we can call that s and raise to the power of n. And this might sound stupid. What's the point of this? Well, if you say the probability of something weird being in the alpha helix, that's one probability sigma of the initiation multiplied by some sort of elongation raised to the power number of residues we have. Remember the definition of sigma here. I might use that. I'll go back and remind you about it. Let's see. You know what? I might jump a little bit forward here. Sorry, I'll do this first. Nope. No, I will have to go back. Sorry. I was saying, my whole point here is that these are going to be very simple parameters that we can actually get from experiments. We can measure, just by measuring with CD spectroscopy, how likely it is to have a helix, how many residues that are in the helical form. I can measure what sigma is experimentally, and I can measure what S is experimentally. And then it's just a matter of, if we know those, we can solve for the initiation and elongation energy from these equations. So we'll get back to that just so shortly. How does the helix form then? Do you think it's a phase transition?
Yes.
What type of phase transition?
Protein phase transition.
And this might be so obvious, right? We've spent the entire morning going through first order phase transitions, and it's wrong. It's not a phase transition. I'll show you why. Let's compare a helix, and this is a long sequence that we have helices formed in some parts, coil in between them, and let's compare that to, say, water and a small piece of ice freezing in the water, because that we know is a real phase transition. The book goes through this in some detail, but I'm going to hand wave a little bit about it. If you have a small region here that has formed ice, the number of particles or water molecules that we have in there is going to be proportional to the volume, which is roughly proportional to the cube of the radius, right, if it's a sphere. The area of that sphere, on the other hand, is going to be roughly proportional to the square of the radius, 4πr squared. So that area is proportional to the number of particles raised to 2/3. But the point here is that the size of the interface between the ice and the water grows as the number of particles grows. If you look at things like such as oil in water or something, having this surface area or something, that's usually bad, right? We don't want to have these areas. So what do you think is going to happen here? In water, this is horrible. This is not going to be stable. And there's a very deep theorem by Lindahl, and that I'm so not going to prove this. Phases cannot coexist in 3 dimensions. And friend of order would then say, but if you go out and look at Stockholm here, we've just had winter, we might still have some water coexisting with ice, right? So what's wrong with that picture? The time constant. So the time constant here might be a month. Rather than 5 picoseconds. But it's not going to be stable. Even if you keep this at 0 degrees, eventually you will have either all water or all ice. You're not going to have 50-50 water and ice. But it might take a very long time to get there. So it's a beautiful example where we have a completely different time constant. But a helix, this is one-dimensional. So if you look at this helix again, the size of the area between, say, the water and ice and the helix, which is going to be between the helical residues and the coil residues, that's 1, 2, 3, 4, 5, 6, 7, 8 residues in this case, right? If I add 3 or 4 residues here, am I changing the area? So that the interface regions in a one-dimensional system is constant. So in a one-dimensional system as a helix, it's perfectly happy to have the 2 regions coexisting. And you can even show this, the number of residues that we have put in a helix here, that means that the freedom here, that would be the number of residues that we have not yet put in a helix. There's n minus n. And this term will always, for a very large number of n here, this second term will always dominate. So the free energy will actually be negative here. So it's very happy to coexist. I'm not going to ask you to derive that. And this is typically what you see in CD spectroscopy. You see helices and coils coexisting. And that's what you see in a protein too, right? You don't have something 100% helix or 100% coil. You have a mix of regions. And for a small helix, you can even calculate what helix length corresponds to the midpoint of the transition, where exactly 50% helix, 50% probability of being helix, and 50% probability of being coil. And that means that the probability of elongating it further at that point should be 0. If we then assume that this helix can start at any point of the n residues, we can finish at any point of the n residues, that's n squared. But we must start before we finish, so that removes half of the option. A rough approximation of the number of ways to put a helix inside n large residues is n squared divided by 2. So that is essentially the volume, and then we ignore the factor 2 because I don't really care about these constants. And then we can show that the entropy of forming this helix is kind of proportional to the logarithm of the number of residues. So I can put that into this equation, what is the free energy of a helix? At the point where I'm perfectly happy midpoint, this should suddenly be 0, so those two things should be equal. And if they are equal, I can say that, well, the number of residues, that's just my capital N there, right? So if I solve for that n and call that n0, I get this expression. The exponential of the initiation cost divided by 2 kt. And remember that I told you to remember the definition of that sigma, the initiation parameter. That actually corresponds to the square root, 1 over the square root of sigma. There's a minus in sigma. The point here is not exactly what this definition looks like. Remember that I told sigma is something that we can measure in a CD spectrum. If you can measure sigma, we measure n. So in 2 minutes in a CD spectrometer, we can measure what is the fraction of residues that are helical. And suddenly, you can use CD spectra to start deriving all these parameters. Just put in everything like the initiation for a typical alpha helix might be, say, 4 kcal. That's a barrier. And the elongation might be in the ballpark of that we gain 2 kcals per mole. So the beautiful thing with CD spectra, we haven't really assumed anything about the atomic nature or anything, right? But you can use simple methods such as speed spectroscopy to peek deep into the free energies, in this case of alpha helix formation. So this is the barrier we need to get over, 4 kcal per mole. Is that a high or low barrier? So what do we compare it to decide whether it's high or low? Sorry? Yes. So it's like 6-8 kcal, 6-8 kt. Physicists, for this reason, they frequently like to think about energies in units of kt. So you'll frequently see physicists plotting and it says kt on the y-axis. So that's 10 kt, which is it's not going to happen instantly, but it's small enough that it will happen. And then once you're over that, and this also, by the time you're at 3 residues or so, then it starts to be advantageous. So you can't form a helix with just 1, 2 residues. We need to have 3, 4 residues before it starts to be stable. But then you can also show that what this leads to is you're going to have a very large range of energies here when you can actually have a coexistence. The helix will form gradually. And this is exactly why it's not a phase transition. Because a first order phase transition was characterized that it has to be abrupt. And then you can, of course, like, why on earth did I go through all the phase transition if the alpha helix does not go through a first order phase transition? But we have another secondary structure, right? Yes. So beta sheets do go through a phase transition. And already now you can always say, remember that alpha helices are super fast and beta sheets are much more complicated. They take longer to fold, but once they have folded, they are very stable. And that has to do with those phase transition properties. The point of this is that a long time ago, people they had this great idea that if you use the CD spectroscopy you can take an arbitrary sequence, and then you start examining what is the helicity, determine this S and sigma parameters for any amino acid. So for alanine, S is roughly, the elongation is roughly minus 0.4 kcal, means alanine likes to be in an alpha helix. Glycine, it's, well, roughly 0.2, which means that it's plus 1 kcal. Glycine does not like to be in an alpha helix, right? So depending on, and proline is going to be roughly 3 to 5 kcal per mole. Proline really hates to be in an alpha helix. So using this, you could actually just add up these free energies, and as a function of the sequence, we could say what is the probability of this particular sequence falling in alpha helix. Don't ever do this. This might get you like 30 to 40% accuracy in a secondary structure prediction. And the reason for this is this only holds for a single sequence in isolation in water. The problem in real life is that you have a mix, right? So first you have real sequences. You're going to have a real protein where things interact with the surrounding and everything. You have all the evolutionary effects. So bioinformatics is going to be orders of magnitude more efficient at doing this. But it might be fun to consider that it's not a coincidence that the reason that some residues like helices and everything, this is something we can measure experimentally. It's not random. It's not purely based on evolution or anything. In practice, we are better at predicting it with evolution. And that brings you to a kind of an important part. When you look at protein structures, there are two ways you can approach protein structure. You can think of this from physics or from evolution. And they're actually orthogonal. One is not necessarily more right than the other, but they're completely fundamental different ways. So if you look at this from a physics point of view, the reason why a protein has a particular fold is it's because it's the lowest free energy, Amundsen. If you look at it from a bioinformatics point of view, you don't really use physics, but what do you rely on in bioinformatics?
One is more probable.
Yes, in a way, but okay, let's dig one step deeper. Why is one more probable than the other? What is the original information you rely on in bioinformatics?
Conservation, like why?
But why are things conserved?
Because
They
they are
exist.
important. The ones
They
that are
exist is a good way, but why do things exist?
Because they're useful, because they
There's one word that describes it all. Why are they useful? Why do they exist? Why do you see them?
Selection.
Now we're getting evolution, right? And the reason why things are good in evolution is, of course, why they are stable here, right? But the difference is that you're going to try to do this with paper and pen now. Nature has had 4.3 billion years of trial and error. That's a bit of a head start. But the reason why things do evolve is, of course, why they're stable and good. But the way, and this it might sound bad when I say it's cheating, but I think cheating is good when you're allowed to do it. By using evolution, you allow nature to use 4.3 billion years of information rather than trying to predict it from scratch yourself, which is a beautiful approach. So the point of an alpha helix is that now we can actually look at the rate of formation. And we can look at the rate of formation because all these energies, we can measure them experimentally. You can measure how fast things happen. We can measure what is the initiation energy. And the initiation, we don't have to measure this with some super expensive time-resolved experiment, right? We take the simple experiment we had, we calculate what is the initiation energy, what is the elongation energy. From those, I could calculate how high is the first barrier, right? And when we calculate the first barrier, then we can calculate how fast do we expect things to happen. And an entire helix forms in something like 100 nanoseconds or so, which means that each residue takes a couple of nanoseconds, say 5 nanoseconds or so to fold. And this turns out to work reasonably well with the things we said before, right? That 5 nanosecond, at this corresponded to an energy barrier, or in the entire helix. This was not something that happened instantly. There was a bit of a barrier for this to happen, but this is still very fast in terms of physical timescales. And so in this case, I would say that this is a characteristic timescale for extending the helix by 1 unit. So what happens is really that you have, depending on what residues you have in your helix, you're going to start from 0, and there is some sort of barrier. You will always have to go over some sort of barrier. And then the possibility is that you might either go down a lot, you might be almost plus minus 0, or you might go up in free energy. And all three are possible. What do they correspond to? Yeah, so different residues, right? Some residues, if you have a polyproline helix, it's going to be the red curve. Polyproline, it's bad to start and it just gets worse extending it. You will never get a helix of polyproline. Not an alpha helix, that is. While if you have lots of residues that love to be in a helix, you're going to follow the green curve. But in that case, there is something bad here. If n goes to infinity, what happens to the free energy? Yes. And is that good or bad? It's not good, it's awesome. It's infinitely good. Can't be too much of a good thing. So what's the problem with that? So that assuming that you already have a helix with an infinite number of, say, alanines, then it would be awesome. What is the probability of having a residue with an infinite number of alanines? That I don't remember but remember what I had the other, like, what is the relative propensity, the relative abundance of various amino acids, right? Alanine might be 10%. So the probability of having an alanine in the first position is 0.1. The probability of having two alanines is 0.1 squared. So the likelihood of only having residues that will form alpha helices is of course smaller and smaller and smaller the more residues you want, right? So in theory you could have this, but the probability of never ever having anything that's bad for a helix, that will also go to 0. So at some point there is going to be an average length of these helices, and that's the reason why you don't see very short helices in nature, because they're not going to be stable enough. You don't see very long helices because they're very unlikely to happen. It's very, very few sequences that could form those. So that's why we actually tend to have helices that are in the ballpark of 20 residues or so. That's kind of the equilibrium, and we might show that tomorrow, or not. It's not super important. You can actually calculate this a little bit more if you want to, but I've taken you through lots of mathematics. I'm not going to do that right now. You can calculate what is the initiation time, and that corresponds exactly to this tau, which is the characteristic time, multiplied by the exponential of the barrier, which is the initiation barrier. And then we can just take the sigma parameter and reuse that definition. So if we know sigma, and we have a rough idea of the rough timescales here, maybe 5 nanoseconds or so, we can calculate how long it takes to initiate a helix. But in practice, if you have 20 residues or so, this helix can start anywhere. And the number of residues in a helix, we had that on the previous slide, that's also related to the sigma. So we can actually, this leads to a small correction, that we can calculate roughly the time we spent to initiate it is roughly proportional to 1 over the square root of this parameter. And then the time it takes to extend this to all other residues can also be calculated from the elongation, and that turns out to be pretty much the exact same expression. But now there are lots of factors too, and everything you've discarded. My only take-home message with this is that an average helix spends roughly half time of first being initiated and then forming, out to 20 residues or so, 20, 30 residues. We have 10 minutes to noon. I'm not going to go through the beta sheets today, but I'm just going to sum up the helices for you. So the special thing, helices form super fast, but they do not form instantaneously. There is a small barrier within the ballpark of a couple of kcals, say 10 kt. And it takes time to start it, but we can't ignore the time it takes to grow the helix. It's roughly 50-50 between them, but both of them are super fast. The beautiful thing is that we can derive all these things from some of the cheapest experiments you can imagine. And suddenly we can actually get numbers for all these free energy barriers. So now we're no longer, and this is the beauty, not just forget about the fact that this happens to do with helix formation. Suddenly we can do some very fundamental theories about how matter and molecules interact, what they should interact. If you then find a simple way to connect that to an experiment, you can use this simple experimental methods to get very detailed information back about the system you're studying, free energy differences in particular. we're likely going to show this for one of the labs, because you might think that this is something simple that people did 100 years ago. I would argue a whole lot of the really cool experiments we and others do today are based on this. You find a simple model that's usually based on predicting a free energy relative to two states, and then you find a way, can we measure how likely state A is relative to state B? And this might sound abstract, but state A and B, you might, for instance, take a protein. How likely, what determines if a protein is a membrane protein? If you can find a way to measure whether a particular helix has inserted in the membrane or not, then we have the relative distribution, right? The second you can measure that, we could do the same thing here, translate it back to energy differences. And then we can calculate whether things are stable in membranes or not. So that, while this might sound and feel like physics, almost all chemistry builds on this. And that's why you keep seeing this RTL and K everywhere. We're inverting the Boltzmann distribution to determine free energies from observations. And the characteristic lengths for alpha helices tend to be around 20-30 residues. You almost never see anything much shorter because they're not stable enough, and you almost never see anything much longer because that would be very unlikely to happen. Tomorrow, I'm going to go through this for beta sheets too, but I will deliberately skip through the beta sheets today. They are way cooler. Lots of mathematics there that I think you're going to be pretty happy that we don't have to cover today. But the summary here is that what I spend most of the time going through is book chapter 8, Statistical Mechanics. Read it, read it, read it. I do not expect you to be able to hand derive all these equations. But what you need to learn here is it's not dangerous to assume things. Equations are usually your friend rather than your enemy. I too remember my second year at university and mechanics, and it was a course in mechanics too even. And I find it relatively easy. But you know what the mistake I did? For every single problem I got, I hand waved, and you kind of get it right. But hand waving only goes so far. And when things become too complicated, you get things wrong when you hand wave. And the point is that equations are your friend because you don't have to be smart. Just follow the equations, let the equations do the work for you. And when you follow the equations, I'm not going to say that you never make mistakes, but you make fewer mistakes because you rely on the equations rather than trying to rely on your gut feeling what you think would happen. And that's something that you should use, whether that has to do with measuring high throughput sequencing, measuring membrane protein insertion, or you don't. The point is that the equations help you. They're difficult the first time you study them, but trust me, they become your friends. I spoke a little bit about helices in chapter 9, but I think this is going to be more interesting tomorrow when we compare helices and sheets, and we're actually going to look a little bit into the coil too. What determines what the coil is? And the homework, I'm not going to have a gigantic list of things here. So the first part of your homework is what I mailed you about yesterday. Tomorrow morning we should talk about this in normal words to see, do you have a gut feeling what all these things mean? What do we mean by the fact that what happens with the number of states when the energy goes up or the energy goes down? All these letters, E, H, S, F, G, what do they stand for and mean, and when do you use F and when do you use G? I already kind of alluded to the stupid constants. They're not as stupid as think, and many of them are actually quite natural. How does these systems' properties change with E or T? Phase transitions, transition rates and barriers are probably more important than the other things here too, because these transition rates are not going to be limited to protein structure. Anything you will ever see is going to be based on a transition rate. For instance, some of the newest sequencing techniques that people are developing in the world are no longer based on fluorescence. Do you know what is the state of the art, or at least in the research when people try to determine sequencing? Nanopore devices. So what you then have is a very thin material. Long term this might be graphene, but today you have other pores. Today you have a very small pore. And then you pull the DNA sequence through this pore. Super fast. It's going to be slow, but on a molecular scale this is insanely fast. And what you then measure is that you measure some sort of property that will vary. And that's essentially going to be an interaction or a current or something. And if we can then determine how does the current vary when we're pulling this through, and that's essentially going to be a transition rate, right? What is the barrier? Does the energy go up or down depending on what you're pulling? Can we calculate how this changes? Ideally, we should be able to detect whether this is an A, G, C, or T depending on how the energy barrier varies when this goes through. I'm not going to cover that in the course, but the point is that these simple things with energies, they are the basis of everything. Anything you observe in a lab can be translated into a free energy of some sort. It's 4 minutes early that I'm going to leave you today. Sorry, I'd hoped that you would get a little bit more time. Do you have any questions for me?